Thank you all for being here today for one of more webinar. Our webinar today is in photogrammetry fNIRs optode registration on the head with the Cedalion toolbox, a tutorial. I guess that's much waited from everyone there. We have two invited speakers, Dr. Alexander from Lühmann and Dr. Eike Middell. They're responsible for that, people for that toolbox. I'm one of the moderators. Cami will also be on the background. So this is a webinar provided by NIRx. We are a company always focused in the high-end solutions and always bringing what's new in the fNIRS field. So that's why we're here today to know more about this new toolbox and what the solutions it can bring to us into the field. If you want to connect with us, here's our social media. Feel free to talk to us. We're happy to receive your email. You can send also an email directly to consulting@nirx.net and follow us on social media. Oh, that's new. We can also just use this QR code and subscribe to our newsletter. We will not spam you, so we will send like 1-2 newsletters per year, and you will see all our releases and every new thing that we have. Some considerations for this webinar. You are muted. Questions are welcome at any time. Please use the Zoom chat. We will get all the questions and we'll talk to them by the end of the presentation. The content will be available online in our website in the upcoming days at this nirx.net-webinars. And if you have any further questions, please don't hesitate to send us an email at consulting or support@nirx.net. These are the people from NIRx here today. Maria, my name, and Cami. And let's talk a little bit about our speakers. Most of you already know them, but maybe there are some things you don't know about them yet. Our first speaker will be Dr. Alexander from Lühmann. He's an electrical engineer from the Karlsruhe Institute of Technology, got his master and bachelor there. Then he got his Doctor of Engineering, or PhD, with distinction 2018 from the TU Berlin. Then he went on for a postdoc at the BU and also visiting research at Harvard Medical School, and did some deep history a little bit in the startup area. He was Chief Technology Officer at Crowley in the US and Singapore. He was also Chief Science Officer and R&D Director here at NIRx for 2.5 years. And he's now the head of Intelligent Biomedical Sensing IBS group at TU Berlin, Machine Learning Department, and BioFloat. He's also still a visiting researcher at the Neurophotonics Center at the Boston University, still one of the lead technology advisors at NIRx, and a member of ISO, DIN, SFNIRS, Optica, OHBM, and VDI, which is the Society for Engineers in Germany, I learned. His contributions to the field have been recognized by the SFNIRS Society. He was awarded Early Investigation Award in 2022, the TU Berlin, the BMOS Graduated School PhD Award 2019, Germany Society for Biomedical Engineering, DGBMT Award in 2018, and IEEE Biomedical Engineering Society. Special feature and cover of the article in 2017. As you can see, Dr. Alexander von Lühmann has a lot of contributions in the field and is heading up to one more. We also have here Dr. Eike Middell, which graduated as an astroparticle physicist. And I didn't know that. Was very interesting, Eike. I didn't know you started there. But it started already with cosmic rays interacting with matter. So he worked with neutrino telescopes in Siberia and Antarctica, looked at optical sensors in large bodies of water in glacial ice to detect the faint light created by cosmic rays particle interacting with matter. Spectroscopy by cosmic rays, mainly. Then he transitioning for a neuroimaging field and joined NIRx. He improved, here at NIRx, he improved the digital signal processing for fNIRS to assess side effects and potential improvements for deep brain simulation for Parkinson's disease. Then he was also involved in overseeing the software development for NIRSport 2 from conception to market release. And he did a lot of freelance scientific software developed consult fNIRS researcher financial forecasting, and also improving the safety of industrial plants using spectroscopy measures. Recently, he joined the IBS lab to develop new methods and tools for the analysis of multimodal biosignals. As you see, we have two very experienced researchers and scientists that are behind this toolbox. So I hope you enjoy the webinar, and again, feel free to make questions at any time. Guess the floor is yours. Alex, you're gonna go first, I guess.
I will, yes, okay. I will take the floor. Let's see. Sharing screen. I see you nodding if it worked. Yes, perfect. Okay, so first of all, thanks a lot for the invitation. It's really great for both of us to talk about this particular part of our toolbox that can do so much more, but amongst others also this. So what I will start with briefly is giving you, let's say, our motivation and why this what we're doing might be useful. So to start with the structure of this workshop, what is not here is the Q&A in the very end, but what we're going to talk about is briefly an overview of this new toolbox Cedalion that incorporates some of the features that we're showing today, a short motivation why one would want to do optode co-registration, a short process overview, so kind of how this whole thing works, but rather on a high level, so you know the most important steps. And then finally, Eike will take over and do a hands-on demo. So we have some, of course, basically we have example notebooks that you can just run by yourself very easily to test out how this works and where you could insert your own scans. And before he shows you that, I'll briefly kind of try to stream some videos. We'll see how well this works of an example scan that our group did. So you see how that scanning procedure looks like. And so just diving right in, briefly about Cedalion. The work that we're doing at this lab is really strongly motivated by trying to move fNIRS more and more out of the lab, which is what, of course, many researchers do, why they do not focus on fMRI research only, but also fNIRS is so we can look at interactions, perception, natural movement in infants, in adults. We can look at movement disorders that otherwise would not be observable really in the fMRI, like Parkinson's, and so on, right? So the challenge here is, of course, that, well, there's many challenges. The challenges are that we have a lot of noise in the data from physiology, from artifacts. We have very non-stationary data. So what's going on in the brain depends on a lot of multisensory input. We have to label experiments. We need to get a better idea of what is going on in the environment. And so there's many ways of tackling these challenges, and really this is interdisciplinary, as we will see. But in our lab, we are trying to tackle this by developing basically equipment that is wearable and unobtrusive. And of course, most of this is focusing on fNIRS. But then also we focus on machine learning and methods that ideally help to explain this variance and the physiology in fNIRS that we can also measure in different parts of the body. And so basically, this is explaining you in one slide the logo of the lab, what we're doing here. And Cedalion is one of the tools, or the core tool basically that we use to tie all of these things together, particularly on the signal analysis and processing side. So the multimodal aspect came already out. We're not going to talk about this really in this workshop much, but basically I'm showing one of these slides that I've shown many times because the idea of getting something more robust in the real world, or even just in very conventional neuroscience experiments, I think circles always around explaining variance in the data, right? And this can be physiology, which we're not talking about today, but it can also come from the sheer practicalities of experimental acquisition. And so heads are different. The cap might sit on the head every time slightly differently, and this will create variance, and it will be very good if we can remove some of that. And this is really one of the motivations why we do photogrammetry. But this is still kind of motivating Cedalion, and so I'm not going to talk much more about this, just to try to say why it may make sense, even if you are interested enough already in photogrammetry. If you want to do more, then the toolbox might also help you to deconvolve brain activity and confounders, both in fNIRS and in diffuse optical tomography, by combining more advanced machine learning methods with the state-of-the-art, say, signal processing and methods in fNIRS and DOT. So this is the last slide on Cedalion. The picture here is from Wikipedia. So Cedalion, you might not know the name, but it comes from Greek mythology, and it comes from a, well, probably normally built human that stood on the shoulder of a giant, the giant Orion, who was blinded and needed a guide to the east. And this was Cedalion, where in the east, Helios restored Orion's sight. So there's also some light involved, which is what we found kind of nice. And why we took this for the name is because Cedalion itself tries to really benefit and give back to all the shoulders of giants that we're standing on. So that's a Python ecosystem. That's the whole communities, toolboxes, and other neuroimaging communities, toolboxes outside of fNIRS. And so basically what you get in the end then is something that tries to tie a lot of worlds together. And what you see on the top here, which includes the photogrammetric Coregistration that we'll focus on now, is standard fNIRS preprocessing and advanced preprocessing, including photogrammetry, DOT, so image recon, photon simulation, and then the whole Python ecosystem of machine learning tools. We work with the standards, bits and snRF, and this is, of course, then also what makes it easier for anybody to adopt methods and maybe use a bit of Cedalion that might be useful, photogrammetry, and take it back into whatever environment you're working in. So if you want to use what we're now showing you, if you want to get your hands dirty, basically you can find the code and the documentation through various means, but the easiest is to go on our labs website, ibs-lab.com/Cedalion. And from there, you find also all the other links. You can also directly go on GitHub, directly go onto our documentation page. You can find us via the Open fNIRS page. There's also a forum, so far not heavily used, but where we also provide some info on how to set things up. So this is where we now start with the actual topic of today, and that is the optode Coregistration. So why are we even interested in that? I guess most people that are joining here are anyways motivated, otherwise I would not be here. But just to kind of recap, we usually start our research planning, our experiments with a research question and a paradigm, which determines what brain regions we would like to target. And now if we have that, then usually we set up our caps. Maybe we buy caps or we print them. So this is some of the work that we did recently. But in the end, we end up with a custom cap that ideally places the sensors over the regions that we are interested in. Now, ideally, what we do after we place the cap on the head is we digitize, so we co-register the actual sensors to find out whether we actually targeted correctly, because otherwise we will never really know. So interestingly, the general assumption, I think in many cases, is that if we design our probe, so this is from Cedalion, let's say we have a high density probe over the motor regions for a finger tapping experiment. We design this on an atlas head and it looks very nice and it's exactly where it should be and it's centered over the motor areas. And now we assume that if we put that on a subject's head, this is in this case 3D, but this is my head, so my anatomy. If we put that in physical now on this head, then we get the perfectly planned probe exactly where we wanted it on the individual anatomy. But in reality, the question is that really the case? And the answer is, of course, it's usually not, because in reality, heads differ in shape and size. The brains differ, and so you can already see this when you look at commonly used atlases like the Colin 27 atlas or the ICBM 152, or in this case the individual anatomy. That well, everything is slightly different. So now the question kind of is more and more rhetoric, but why Coregistration? If we measure with fNIRS, then it does matter where the sensors are. It's not EEG, where we have through volume conduction a lot of spatial smearing, and we can measure a lot of signals on different parts of the head simultaneously. So it does matter where we place our probes, and this is relevant to see whether we place our probe correctly within the subject, but also within the group of subjects. So how this probe movement and the targeted brain areas or the measured brain areas, how those differ. Just to give you a visual example, because we talked about finger tapping now, if we have this probe here and we're actually interested in the blue area here, but the probe shifts because just of the shape of the head or the way the cap is worn, then the kind of this channel that we're looking at here, the green dots are the channels, is going to move basically with the highest part of its sensitivity to the somatomotor area, which we're interested in, to the dorsal attention network area. So, and of course, our resolution is maybe around a centimeter, so there's some wiggle room. But just to make clear that it can actually matter, even if you move the whole thing by a centimeter, you might see less of what you would have liked to see, that you thought you would see in this channel. And so this is, of course, known. So we're not talking about anything new. This has been known for quite a while, and then several groups in the world have used different kinds of co-registration, including the Polymus fast track, which is field-based point-by-point sensor. You have to really go to each individual electrode or optode. If you have a hospital or a lot of money, you can use optical surgery navigation systems. But then, of course, now the field has more and more proposed photogrammetry approaches. Here, this is Robert Ostenfeld with the field trip toolbox. Then here we have another journal, JBO paper, and then from Rob Cooper and Sabrina Brigaroy in Science Reports, another paper that just shows this actually works and it improves outcome. So this is basically just the main message why we're here. So we go into how to do this. But just to recap, for fNIRS, it means that individual channels, if we don't have a high density probe, then we can rely a bit better on whether the channel or a few channels we're really measuring over the brain area that we are interested in. In DOT, we can also get a better spatial reconstruction. So if we know the actual placement and we look at the sensitivity profile that we can calculate from this, then especially ideally on an individual anatomy, but also on any other, we're going to get a more accurate outcome. And then with that, for example, what we get is this here. This is again my brain. This is during finger tapping, and this is with a co-registered probe. You can see it by the messiness, basically. It's not really a perfect pattern the way we had planned it. And you see that the activity of my finger tapping is actually pretty much where we expected it to be, but the patch itself we had actually centered with this centered LED on top of the actual area. So we can see the patch shifted, and where we will now see the activation, I mean, if we don't do image reconstruction like this, if we look at single channels, will be slightly different from where we thought we will see it. So just to show, even in our example, this was not planned, right? This was just kind of, we do finger tapping, we do co-registration. Afterwards, we see, well, the patch was not really centered where we thought it would be. Okay, so what's the process? So I guess people are mostly interested in how to do this now. First of all, big thanks. A lot of the foundational work that was done here is originated by Philip Jenko's master thesis in 2023, and then polished and improved a lot by Masha Yudina, who was a BCCN lab rotation student here until early this year. And so what you're going to see now is the high-level overview, the steps that we'll then show you a bit more in detail. The first step is of course, the physical preparation of the cap. We'll see this in the video, but then the actual scan. We'll come to this. We're using a specific device here. It's really not dependent on this specific device. It's just a device that we found works for us, and now we're using it. We do need something else than this device, and that is we use a colored label stickers on top of our NIRx spring tops, because this is then later on how we identify automatically the surfaces and the actual positions of the optode. Important here to say maybe is that we want to use colors that are not already everywhere on the subject or in the room, specifically on the subject. And it does help to use very strong colors or neon colors, because those are usually not everywhere already. In this case, yellow works very well for us, but you can use neon green or something like that as well. So then after the scan, there is something that is pretty much vendor or solution specific. So if you have a Einstar 3D scanner, then there's a software that basically does something with the point cloud from the scanner and gives you an object that can be further processed. If you use a mobile phone, then that will be the software that you're using that creates that mesh and the cleanup. And we'll go into some details for this as well. And then we're already at the point when you have your object. That's a file, that's a mesh that gives you the structure of really the scan and the texture. If you have that, then you can go into Cedalion, where you first load this object. So that's really basically it. So you load the data, and then you will have to set manually right now the hue saturation value thresholds for detecting the optodes. So basically the colors that you chose, if this was yellow now in this case, it will of course be a bit different depending on the lighting conditions and so on. So it will not be just one single point in the whole color spectrum, but it will be a spectrum, a window basically that we need to identify. And this is something that gets manually typed in by you. And then you select landmarks on the head. This is the reason why we often put, you will see in the short video, little labels that later on make it easier, but you don't need those, because if you're good and practiced, in finding these landmarks on the head, you can also just do this here later on without any green, sticker on the landmark already. And what then happens is you have your montage, you have your originally planned probe layout. In our case, this high density NIRS2 bilateral probe. So we need a probe layout that can come, for example, from the SNIR file, because that gives us the kind of intended structure, but also the labels, right? So detector 1, source 1, and so on. And then what happens is an alignment basically between the scan and the actual probe layout that gives you then the labels of the identified positions. Something that happens here that you'll see later in the example a bit better, because I can't move in 3D here, is that what we first detect is the surface. You can see these red dots here. They are detected by the algorithm, so these are inserted and shown. This is basically the detected optode surface. And then from there, we project onto the scalp, knowing the geometry of the NIRx optodes. You can also, it's kind of optode unspecific, except that there's a certain value from the surface to the scalp, the distance basically that has to be used to project along the normal onto the surface of the head. And then these get the labels. So now, right where we detected detector 3 here on the surface gets projected onto the scalp surface with D3 as a detector. And that then gives you your head model. It doesn't have to be an individual one, it can be any column, ICBM or so, with the co-localized projected detector and source positions on the surface that you then can use for moving forward with your analysis. So just briefly about how we evaluated this, there has been a lot of stuff going on, but one of the ways that we did it is that since we know these head models, we can also just print them. Then we have a physical and digital ground truth that are pretty much overlapping. So here we used the 1020 coordinates or 1010 coordinates, and we placed the detectors directly exactly on these spots, which are, because it's a 3D model that we have, we know the exact coordinates. We place them, we scan them, we get the estimated positions, and then of course we can compare how well in this way of evaluation, we also did others, but how well we actually map from the actual measurement to where we kind of know our ground truth should be. In that case, we're around 1.6 plus minus 0.6 millimeters exact. Other scans where we put it on subjects' heads, we checked, of course, there we don't know the ground truth on the scalp. We looked at how well we get a scan, rescan precision. So basically put it on the head. You don't take the cap off again. That's also possible, but that's a different problem to solve. Scanning it again, looking at how, we always end up with the same result. So you get around a millimeter. Now, briefly, a bit of a technical workflow, and then it gets more intuitive again. So what's 2 steps that happen, and what are the dependencies here? During the measurement, but what do you need? You need markers on the spring tops and your landmarks if you want to. You need even lighting, ideally, in the room. So from all directions, there should not be strong shadows, because those will turn some of the label colors darker, for example, and make them harder to detect. You need some scanner. In our case, it's a 3D scanner from Einstar. In our case, because the Einstar scanner is quite powerful, we need a strong PC, but if you use a mobile phone, for example, that is also sufficient. The scanning procedure, if you know what you're doing, takes between 3 to 5 minutes. So that is the actual scan, not the physical setup, but the physical setup is the same as if you would do your normal experiment. And then after the scan, you do this post-processing in the software that creates meshes, fills holes, for example, and kind of cleans the whole thing up. And then you can export this And what you get is an object file and a PNG file, so the texture and the actual object and the mapping between them. And that goes into Cedalion. And so what happens here first, and you will see this in the example, is we detect the optodes first. So these yellow circles in this case, or any other color. For this, you need the input. Basically, you know, what's your color that you want to detect? You then can correct by adding or removing optodes that were detected. So maybe sometimes the light was not good or something else was in the way. Maybe some optodes will not be detected, then you can manually add them. Or if something is going wrong and it detects something that's not there, you can remove it, which just means if you do a good job in preparing and scanning, you have really no manual work to do. And the more messy the scan is, the more manual correction you have to do afterwards. And then the Coregistration happens, where you need your montage and the scan, which if everything goes well, which usually it should, you get the correct labels and you're pretty much done. So that can save then the 3D positions with the labels, the detector source labels and so on. If this does not work well, for example, because you really mess something up with the cap and the landmarks, there is a way of doing another cycle by ignoring the landmarks and instead selecting optodes. If you know the labels of the optodes, you have designed the experiment, the whole thing can still work. It will tell you which optodes to select, source 1, detector 5. And by doing that, it will also find a transformation that should ideally end up in a successful co-registration. Okay, so which scanner to use? I already mentioned we're using a commercial 3D scanner, and this is really no advertisement for them. By now, probably maybe you find something cheaper that is at least as good. It was just simply that we didn't want to take too many risks. So we said, okay, we take a scanner that has a rather good resolution. So 0.1 millimeter is really much more than we actually need. And that has a good scanning distance and you know, size of things that you can scan. But it seems, so we're not currently using this much, but we know it from the papers, and one of our PhD students has done this a lot. You can also use mobile phones with an app. Now this will then depend on what phone you have and what app you use. So some phones have true depth and LiDAR technology and so on. And then depending on the apps, whether they use this or not, you get a better or worse resolution. But just from this paper recently here, for example, you get an idea that from this paper and the examples they gave across different solutions, you get something like a resolution from 2.2 to 4.4 millimeters, which is worse if you look here, but it is to some extent very likely still sufficient. And unfortunately, we can't tell you really, what's the best solution, which phone to use, which app to scan. But in general, the statement here is that what you get out is the same. You get an object file, and that can be loaded into Cedalion. And that can most likely do the job very, very similarly well. So this hands-on demo is pre-recorded just for the sake of time, because we want to see, sorry, there's two parts of this hands-on demo. So the first part is pre-recorded. The second one is going to be done by Eike. The pre-recorded is mostly, because of time. So we'll be able to skip a bit through. So here, big thanks to a postdoc and 2 PhD students in our lab that kind of did this for us, who you will see now also in the recording. I have to switch back to my pointer. Get back. See. Okay, so I might skip a bit in between, but what you see, what we do first is just measuring head circumference and choosing the right cap. So if this is like a textile cap, then for example, it's this. Then you see we're actually not putting that cap, we're putting our own Ninja cap with the motor probe that I showed you previously. So that's basically what we're going to use for the example. What Niels is doing now, he's putting these landmark stickers that I already mentioned are optional, so you can, but you don't have to do it. It's just, if you're better in selecting landmarks on the actual head by feeling really where the nasal inion and so on is, then maybe you want to do this. And otherwise, you can also do it pretty much to your best knowledge on the scan itself. Okay. So NIRx is also placing 2 in the back of the head. We don't really need that anymore. We had originally something, I mean, it can be useful, but to kind of detect automatically where's front and where's back from just points. But what happens then, and this is again, you know, generally, regardless of whether you do photogrammetry or not, is a good idea. If you know where the CZ point, the midpoint on the cap is, you want to find that point and then you want to readjust the cap so that it is actually sitting the way it should be. So we see here now it needs to be moved forward a bit. This is not photogrammetry specific, but kind of a good practice. And so this is still kind of preparation. Then what's quite important, I mean, in general, cable management is important. I guess you will have learned this from all the NIRx trainings that you might have ever gotten. Cable management in this case is also important because we don't want to have the cables in the way, right, in the scan, which will cover some of these labels, which makes it harder to automatically detect them. And so then this is just a setup of our scanner. Again, depends on what solution you want to use. Yeah, this is again is vendor specific, right? But we start a project. You can see already that we select a specific resolution. You can go down to 2.2. We say like 0.5 millimeters for sure enough. And then there are some settings like, you know, how bright the whole thing is, what's your working distance, and so on. And then the scanning starts. And that I will basically fast forward because, I mean, we can wait 3 minutes, it's actually only 3 minutes. But what you will see on the screen later on as well is, well, it basically partially creates this point cloud of the surface that gets mapped in the software. And then once the scan is completed, that gets converted. So NIRx is just going to walk around Bilal here. There's a specific distance this is ideal. And then if you're getting too close, in this case, the software will tell you, you know, move a bit away. Just skipping this a bit. So you see there's a bit of scanning going on. This scanner also has light to make the lighting conditions a bit more even. And then now what we do is we check briefly the data quality. So you can see this is the scan, there's some holes. And if you turn on the data quality indicator, the darker regions maybe didn't work out so well. Green seems perfect. And so then what NIRx will do now is he says, okay, I scan a bit more. And he has to align these again. So in the software, it will tell you basically if it found certain landmarks, now it's snapped, just see that. And so now you can start scanning again. And you'll move over that part of the head that didn't work out so well. Just gonna skip that for time reasons. And then the next step here is really that he presses optimizing and generating point clouds, which just in this software will create a mesh in the next step that, for example, fills holes that you know, you will see here the underneath the beard is in the ear, right? There's holes, there's nothing, and that will be filled. That will be visible after the meshing is done here. So now you can see mouth looks a bit odd because it's kind of closed, but the whole mesh is kind of a clean mesh now, which doesn't have holes, which can be saved. So we save STL object PLY just to be complete. And yes. It was an awesome subject. So that is basically pretty much it for the actual scanning procedure. And fast forward here was only you know what I scanned, skipped a bit of the scan, and I think the meshing was fast forwarded. It takes maybe a minute or so, but yeah. So that's the scan. Okay. So then very similarly, and I'm going to go even a bit faster over this. Is, for example, with a phone. And again, like just a statement here, we're mostly working with a 3D scanner, but papers, you know, all tell you that phones are fine too, and you just need to find your solution. But it's pretty much the same thing. There is basically this walking around the head with the phone. In total, similar to duration. We don't really have a data quality report here maybe then, but you can tell he kind of tries to get all angles once. And then this is an iPhone 14, by the way. And then, yeah, so then he's done. And he's basically creating the scan from all the photogrammetric recordings. And well, looks good. Okay. Let's save it. And then we're done with that part, which really, you know, I can only tell you, you kind of need to find your own solution, or you just copy what we've done. But this is basically where we can only give so much instructions. Just to repeat, important is that the lighting conditions are good and the cables are out of the way. So, and now we come to the how to do this in Cedalion. So if you have your scan, you have your object file, and you want to try it out, we have this documentation page, which I linked to earlier, that you can find through our website or through the GitHub, where we have examples, and these examples will show you pretty exactly how this works. You can run them. So this is rendered on the website, but if you get the toolbox and you have any Python environment, you can just run this as in a Jupyter notebook. There will be example files automatically downloaded, like a scan like this one, and you can basically try it out step by step, and you can just replace the file and see how you can adapt this example to your own needs with your own scan. And this is now where Eike will show you how this exactly looks. But just to show you kind of before I hand over this one other kind of example. So our friends in Boston are using this right now also for whole head scanning, which seems to work quite nicely. And you can see they use two different colors, something else to be discussed. So these two colors here, this is something that Eike will show you now, can be selected by looking at the overall range of colors available in the scan and trying to find the good window through these parameters that then, if they are chosen well, these red dots with the spikes will be found very well. Okay, so I hand over to Eike for the actual hands-on.
Thank you. Just a moment.
Stop sharing.
Start sharing.
That
I
worked.
hope you can see my screen. Okay, great. So what I would now like to do is to walk you through one of these example notebooks that show you the different steps how actually getting from the 3D scan to a probe geometry, how that works. And as Alexander already pointed out, these example notebooks also form our documentation. So you will find a rendered version of that on our website. But if you want to run by yourself, the first important thing that you will have to do after importing Cedalion or sub-packages that are needed is that you have to decide whether you want to run that notebook in interactive mode. For the documentation, we just render static pictures. When you have the notebook on your own machine, set it to interactive because the 3D visualizations are interactive. So after you have chosen interactive true here, the first thing that you have to do is you have to load the triangle mesh into the notebook. If you don't have one by yourself, you can use functionality from Cedalion.datasets to load an example scan. This is what we're doing here. So if you load it, what you will get out is a surface object that contains here plenty of vertices, the triangle mesh, and this is what we will analyze. So it's textured triangle mesh, meaning that each of these vertices has a color assigned. If you want to load your own triangle mesh, you can just adjust these passes here, and then these will then your own file will get loaded. Then the most important part here is that we have to analyze the triangle mesh in order to find the location of these stickers. So there are vertices in this mesh which have this bright yellow color, and these we want to identify and then label as optodes. To that end, there's a class called colored sticker processor, and you can configure it by giving it color ranges which vertices you would still consider yellow enough so that they should belong to the sticker. So here we say we define a class, call it O, like optode, and define in hue and value, so two parameters in the HSV color space to specify the colors. I will visualize that in a second, then it will become more clear. However, as soon as I have specified that color, I can then ask my processor to process the triangle mesh, and what I will get out are the sticker centers and the normal vectors and the details object, which tells me, which gives me more information about how the process runs. So what is the result? The result, as I said, are the sticker centers. These are stored in Cedalion in this data structure here. This is the X-array data array. So here you can find now all the positions and the point about these data arrays is that for each of the found positions, we also have things like labels, like each optode at the moment gets a generic label, like something like 028, 005. And at the moment, it's an unknown point. We can also visualize it. We are using PyVista as a package to do 3D visualizations inside Jupyter notebooks, and we have under Cedalion plots a number of functionality to plot triangle surfaces, labeled point clouds, and also vector fields. And if I put into this plot now here, the surface mesh that I loaded, the sticker centers that I found, and also the normals that I found, then you get this result. Just a moment, let me scroll down. So this was a scan of this 3D printed head. We labeled the landmarks here in green, and we asked to find these yellow stickers. You can see here that the 3D scan didn't catch everything of the optode, but that is not important for us. For us, it's really only important that we get this yellow plane of a sticker in the space so that we can find its center and that we can really find the normal in order to down project onto the scalp. And as you can see by just rotating that head, the automatic detection here did a fine job of really finding the sticker centers for all of them. The details object that I mentioned in the beginning comes with some plotting functionality to give you more insights how the classification actually worked. So what is shown here are the two color parameters, the value and the hue of the color in order to specify which color a vertex has. And you can see here the range that we have specified in order to classify vertices as yellow. So every vertex that falls into that square, to this range of values and hues, this we still consider and selected by that. You can also see the whole HSV color space, but typically the hue and the value is what's most interesting. If for your own mesh, for some lightning condition, you notice that the automatic sticker detection doesn't work, then these two plots give you the best chance to correct something, because you will notice that you will find vertices outside of your selection area and can then adjust them. Also, these next set of plots show you for each of the sticker that we identified their position in the plane that we identified. So if these all look circular and nice, then the detection actually worked quite well. And as you can see, for most of our stickers, that worked nicely. It can happen that not everything gets detected automatically. For these cases, the notebook also provides interactive ways of removing optodes and putting them back in, but this is not necessary here, as everything worked fine. Next thing, since we have a position and since we have a normal vector, it's quite easy to project down to the scalp. This is done here quite easily. We specify the optode length, which we know because we can measure the optode when it's not inside the cap, and then we can just subtract the sticker center. We can subtract from the sticker center a vector of the optode length times the normal to get down to the scalp. So these are here in this plot, the greenish dots. The red dots were the one that we found. So these are the sticker centers. If we now follow the normal down to the scalp, we get these green dots. And these are interesting because these will be really the positions on the scalp. However, up to now, these positions that we identified on the scalp don't have labels yet. They all have these generic labels like 028, 005, because up to now, no montage was considered in the whole process. Next thing, we can specify landmarks. This works similar like the optode selection. We can right-click in these, right-click on the 3D plot. The first time you plot, it puts a marker in there, and then you can, by clicking again, it cycles through to adjust the label that you would like to assign here. So this over here should be LPA. As soon as you have these landmarks and also packed them into the right data structure, now comes the interesting part, because you'd have from the scanner the sticker centers and the positions on the scalp derived. If you now take a recording, for example, with Aurora, and you have used NIRS to specify your montage, then the SNIRF file that you get out of Aurora also contains 3D positions of your montage. However, these 3D positions, these have been specified on the ICP M152 head. So this is a different head geometry in a different coordinate system, but it has labels. So what the next thing that we want to do is we want to take these 3D coordinates, try to find the best transformation how we can make these two point clouds match, and then just transfer the labels from the coordinates in this NIRF file over to our scanned optode positions. To that end, we are using again functionality from Cedalion IO to read this NIRF file. What we get here is the so-called Geo3D object. So this is an array of coordinates of our probes and landmarks. And one thing here is really that one has to take care of not confusing coordinates from different coordinate systems. So the Einstein scanner uses a completely different coordinate system than what NIRS does. So if you just plot them into the same coordinate system, then this is what you get out of this NIRF file. So here these red and blue dots are the optode positions, and these black lines here are the line from NZ to IZ, from Nersian to Indian, and the LPA to RPA line. And if you just plot the landmarks that we got from the scan, these are located like that. So you have these two different coordinate systems and you have to find a transformation to make them match. But since you have these landmarks, that's easily done. So here we derive a transformation, we apply the transformation, and afterwards both point clouds are in the same space, here plotted onto the same scalp. And then the final step is that we are now trying to find which points belong to each other. So you have 2 point clouds which are very similar to each other. There's still small deviations because the ICBM head and your subject head have a different geometry, but in principle they are quite similar. So what we are now using is an iterative closest point algorithm in order to find the best match so that we can then afterwards take the closest point and transfer the label. And if that all works nicely, you will end up with a plot like that. So here on the left-hand side, we see a 2D projection of the optode positions as we got them from NIRS out of the SNIRF file. And here on the right-hand side, we see the same projection method applied to the scanned coordinates. You can look one-to-one that the optode labels match. So this cross-check manually is helpful to see that there are no errors. And what is color-coded here are the channel distances between the different optodes, and just by a quick comparison of the colors, you see that there have been deformations because the subject, the scanned optode coordinates on the subject head are different than what you had designed on the template. Last but not least, there is one alternative approach. We use these landmarks at the moment in order to derive the transformation, which brings the two coordinate systems together. If you don't have a good estimate of the landmarks, then you could also use some optodes for the same purpose if you know which are they. So in that case here, what that example notebook shows is if you load a visualization, a 2D visualization of your montage, you can then ask Cedalion to find a good set of 3 optodes which are quite far away from each other. So what it does, it looks at the montage in this SNIRF file and determines that source 1, detector 30, and source 31 are good candidates. So source 1 is over here, detector 30 is over here, source 31 is over here. So these are 3 points on the head which are quite far away from each other. So and it will then give you again the chance on an interactive plot to select these. And if you right-click them, I've done that here already, then this gets these larger sphere markers. So you can select them and afterwards use those in order to derive the transformations with the same result. So in that brief way, I hope I gave you an overview of how the process actually works in that notebook. Maybe one last mention, we develop Cedalion really in a bottom-up approach. So our idea here is that we are building very many small building blocks from which then solutions, like solutions to that photogrammetry problem, can be built. And one advantage of doing it that way is that by providing you that notebook, you now have something where you can really look under the hood how it's working, but also adjust it if your needs are different. And with that having said, I'm done.
That means we are pretty much open for questions. Maybe one thing I can take already away is one last thing, which is then also the slide on, before the slide we finish, you should see my screen again, which is if you want to anonymize your subjects. So we have this little example here, which is if you use any tool like MeshLab, there's open source tools to load your object file, you can easily just cut away those parts that are identifiable, also the parts that you don't need to make this, the mesh smaller. So you can just cut away the face. What is actually in this example not perfect or not ideal, but I think you can translate mentally, is you don't really want to cut away the Bayesian landmark, but just to show you how easy it is to cut away basically the face, and you can save that and then do the whole thing on that mesh, given that you keep the landmark. So this is kind of not ideal in this example. Well, okay, so and now I think just a brief thanks to everybody in our lab and also for the invitation, of course. So everybody that contributed, this is an older picture here, but and with that, I think we are open for any questions.
Thank you very much, Alex and Eike, for the presentation. So indeed a very important topic for more reliable and robust fNIRS measurements. So thank you so much for working on that. I guess one of the questions we had before that came through the registration was exactly that. How can I keep, raise this issue of people that don't consent to video or data privacy, how I would deal with that? So I guess you kind of answered this question there. So that's done. I am not, someone sent a question here at the Sagar. I'm not sure. What is your, during the transformation to write to NIRS site or Aurora with the real-time scan file, it's only taking the reference for names of location or also making some adjustments in the location itself, the important montage. I guess you have some questions on the NIRS site directly. Is that correct? How the NIRS site?
Am I audible?
Yeah.
This is Sagar.
Yes.
Yeah. So it will be
Hello.
better if I ask this question directly. Yeah. So what I wanted to ask is, when Eike said that we are importing the montage from either NIRx site or Aurora, right? Yes. So is it only taking the reference of the names from the montage or also making some changes in the localization of the scan file also?
What I understand what you mean. So what you get from NIRS side, if you design your montage in there,
Yes.
is are 3D coordinates of your montage if your subject would have the ICBM head, right? And these 3D coordinates are then also stored in every SNIRF file that you are recording with that montage. So what we are taking is we are taking these 3D coordinates with the labels. So also the labels are specified in your site. And especially these landmarks are then used in order to match the optodes from your site with the one that you have scanned. Because this is a common, the common piece of information that you have in both. You have the same landmarks with the same labels, but in different coordinate systems. And these are then used in order to find a transformation which makes a match. So then you have two sets of coordinates which are quite similar already. And then the last step is really only to find that mapping in order to figure out which label from the NIRS side coordinates you really want to bring to your scanned optodes.
Right. So let's say if there is some minor difference between the NIRS site montage and the one that we scan. So let's say if there is 2 millimeter difference. So is it going to take an average or half of it, or which is the preference? Which is the
know.
preferred? Yeah.
The position comes from the scan, right? Because that's the real, experimental setup. And so those will not be moved. The only thing that is used from the montage is the labels to kind of assign the proper optode to the found optode.
Right. So it's only basically the labels that is taken, but the scan file will not be changed with respect to the montage that we imported. Got it. Thank you.
Thank you. We also have a question from Cecilia. I don't know if you want to make it yourself, but I can also. Yeah. Okay. Feel free.
Yes, thank you very much. So thank you very much. I think it's something that the community is waiting for a lot because it's user friendly, so to say. So thank you very much for tackling this issue. I had actually two questions. First question is, how much do you need the scan to be of the entire head, like the whole sphere? Because I'm thinking typically, let's say, coma research or patients who lay on a bed or sleep research where it might not be possible to get the full sphere when scanning. And another question is about motion. So let's say you have people that cannot refrain motion, either because they have Parkinson or motor disease, or infants, babies, children, whatever. How tolerant, how resistant to motion is the scanning procedure?
So, Eike, do you want to take one or two, or I can take also both? Yeah.
So about the partial head scan, so what you at least need is 3 points that span up, so that are not in the plane, right? So I guess that if you get the LPA and RPA and the Anonymization, you all are already quite good in order to get that alignment. In principle, there is not much more in the method that really needs all of the head. You really only get, so what you will get is that partial scan, triangle mesh from the scan, and in order to orient that, these 3 positions should be good. I could imagine that using some more landmarks could help. They don't have to be on all sides of the head. So for someone who is lying in the bed, I would guess that should still work, with the caveat that we haven't tried that out.
Yeah. For the second question, I mean, we have not scanned infants, for example, now, but I think the big difference there is that if you use a more or less professional 3D scanner, we saw this in this one video, there is this kind of tracking, so that the software finds some landmarks that if you lose, so basically if the tracking of the object to be scanned and the object in the system is kind of off, then it's going to tell you, so you get an alarm basically. And I don't know if you remember, I can try to pull it up just amount of time. So what means that if the subject actually moves in between, right, and the tracking is lost, you could find it again. And this is what happened in the example where Niels stopped the scan and looked at data quality and then come back and scan the rest of the head. So I think with such solutions, you can at least partially compensate for motion. Of course, during the scan, it does help if there's not too much motion. I mean, we have not investigated that, but I would say that probably helps with a lot and might be trickier if you use purely photogrammetric scans, in the software. Sorry, on the phone and the software.
And a bonus question, does that make a difference in that term, whether you use a phone or the scanning tool that you showed at the beginning?
Yeah, I mean, so, I mean, from our experience, or my expectation right now would be the phone. We don't have, you know, we have not tried all the different solutions, but my understanding right now is that the this kind of tracking is not per se there, right? So basically the subject needs to sit still. In the 3D scanner, in our case, at least it is. So I think probably there is or will be sophisticated solutions also that are completely, you know, software based on the phone and might be able to catch, you know, the same landmarks again, but you know, this is really where we don't have much experience. Just to say that the scanner that we do have enables you to stop and you know, start again, and so, and you know, to find where you left off. And so this is where I think that this could compensate some of the motion problems.
Thank you very much.
Okay, moving forward with the questions. Other questions. Alena sent a message here, said, thank you for the presentation. How much time does it take approximately from beginning to end? I guess, I mean, you talked about the photogrammetry. I think she's talking about the part in the programming where you have to do the reconstruction.
So there's two aspects. The one is, I mean, in total, it does not take very long, right? The things you could say you could just run it through, but you can't run it through because there's some interactive, you know, stopping points, which Eike showed. So landmark selection, maybe looking at cleaning, you know, what optodes were detected or not. And so this is really what determines the overall time. So I mentioned before, if you have very good lighting conditions and your scan is a good scan, or like very good, like, you know, you took proper care of like equal lighting on all sides, then the manual interaction is quite limited. You don't have to do much. And then it's really just a runtime of the software, which is, you know, it's Python. Loading a bigger file takes a few seconds, and then you're running these things. So in the end, you know, it's, I would say maybe 1 to 2 minutes or so. But then, of course, if you have a lot of optodes and some of them were covered and are not detected, and you need to manually correct that, you need to do it only once, right? The result you can save, but then that will take you more time. But just to say, the scan itself takes, let's say, 3 to 5 minutes if everything else is set up. The software of the, you know, vendor that we're using, of course, the meshing and so on maybe takes another, let's say, 5 minutes in total if you do, you know, put the right settings and you let the whole thing mesh and export it. And in Cedalion, it basically is running the code, which is not incredibly slow or, you know, complex, and really depends on how much time you need for the manual interaction, for the landmark selection and the, correction if necessary.
Thank you, Alec. One more question, Catherine. I don't know if you want to unmute, if you want to ask your question.
I don't know. Can you hear me? Because I don't have a headset here.
Yes.
We do hear perfectly.
Yeah, so I mean, I'm super new to this, so this is probably obvious to some of you, but I just ask anyways. How would you map the subjects onto each other? What software do you use? Because then I have kind of like geometry of everyone, and how do I do the group analysis then?
So that kind of, it goes into different directions, but I mean, in the end, one direction is, of course, if depending on the toolbox that you use and so on, you know, you want to end up in brain space, right? So what ultimately people wonder about is, of course, if the same brain area lights up for each subject. And so that is really about, you know, finding the right transformation using, you know, free surfer brains or MNI coordinates or so. And so right now, we don't offer that yet. So we're working on some things like this, but basically working on the same brain coordinates is something that is what you would want and that we're working on, that we'll also provide eventually. Right now, I think what you can only do is you can compare variability between optode position and compare, let's say, 3D coordinates on the atlas brain. So if you use the same brain, if you don't have individual MRIs, right, then you can, of course, compare basically in the same 3D space where your probes were and how much coverage over the same brain areas are there. But if you use individual brain anatomies, then you need to go into parcel space, or, you know, the space of, you know, brain areas that are defined by some coordinate system that you prefer.
Thank you. Yeah, I wouldn't be having individuals MNI like MRI scans. Sorry, but so is there actually a tool out there that can get me from the optode locations individually to the standard brain?
To the standard brain. I mean, so
To the
we are.
MRI space or something.
We will be eventually. Other tools, I don't know which one to recommend, so I don't really know. But I would just say as an in-between solution, what is kind of also interesting is, of course, that with Cedalion, what you can do if you're using the same atlas and you have these different probe and basically the same head, at least on the atlas, with different probe positions, you can of course calculate sensitivity profiles, for example, and look how those change or differ between subjects. And the sensitivity profile tells you just how each brain area, how a change in a certain area of the brain is going to affect the change in the signal that you see, and that can also directly be compared.
Okay, and then maybe just another quick one. So does this then get me at some point like an individual partial path length factor, or do I have something wrong now in my mind?
Individual partial path length factors, for that, I think you would need individual anatomies.
Even still, even though I have, because what I just saw in the demonstration, it would have been that you kind of like had this, okay, how far the optodes are from each other, and you could then theoretically calculate something from that, maybe?
Yeah,
not?
sure. Yeah. I mean, you could do that also on the atlas, and of course, you can get that. But then, what you kind of, I think at that point, I don't know what you need them exactly for. So I think one of the recommendations is to use more like a normalized, you want a HPO and HBR distance dependent, and so we are interested in how far the optodes are apart from each other. And if you use now an atlas, you could calculate, let's say, the banana and the path length, the partial path length. The problem is that then you're using the same optical properties in the tissues of the atlas that are then not individual anymore. So to be honest, this is where I'm not sure what's to gain and what to lose. So I think actually I stopped talking. For sure, of course, you get a better estimate because the actual optode positions. But as long as you're working on an atlas, I think there's some limitations of what this will yield.
Okay, cool. Yeah, thanks a lot for the clarification.
Thank you so much, Catherine, for your question. Thank you for being here also. We have one more question from Til Sander. Would you like to unmute? Otherwise, I can talk.
Sorry, so this is okay. Here I'm from PTB, from magnetoencephalography, and quite often now this is about LPA and RPA, which really are not well-defined anatomy. So I'm a physicist, but not an anatomy person. Anyway, but this tragus incision, which is kind of the indentation at the lower earlobe, this is quite often used in MEG. Did you ever look for that in your optical scans, if it's identifiable?
I mean, if you could identify this just from the 3D scan and put that as a... I can't say we have. I think the general point is that you could adapt all of this. The point is only that your montage, I mean, basically you need to matching landmarks in that you select and in your montage that you use to transform both, right? The planned montage and the measured one. And you could actually pretty much use any kind of landmark as long as that's consistent. And this is what Eike also showed. If some other things fail, you can actually use the sensor locations themselves as landmarks, basically. But Eike, you unmuted.
Okay, makes sense. Thank you.
I also just wanted to point out that in this whole process, the landmarks has a very small role. They are really only giving you this rough adjustment of the scanned optodes to the one that you get from the tool like NIRS side. And then the fine adjustment is done by the iterative closed point algorithm in order to find what is the best match.
Okay.
So I guess these small differences won't play a role here. In other regions they might do, but I think for that application it's really not a big thing.
Okay, thank you. Sorry.
Thank you so much, Til. Okay, I don't see any other questions. If anyone has any questions, feel free to unmute yourself also at this point. I'm just checking the questions we had before. You have answered most of them. One that's still there, I guess, does it work with Android-based devices? Have you tested that?
So we have not tested that, but I think the statement also from our PhD student who has used more like in his own project more phone-based photogrammetry. It depends really on the software, and there's different kinds of softwares. And in the phone, I would right now not know about any limitations, except that I think the iPhones were a bit faster in providing additional structured light or so. But also that is not necessary, right, to do the scan at all. What we cannot really quantify right now for you, because we have not, we have used our 3D scanner, is kind of what's the worst and best phone and software kind of to use. But I think it is worth trying out, even if with the phones that you have in your lab and some of the open software.
Okay, thanks, Alex. Yeah, most of the question exactly on this line, like minimum hardware requirements for using the Cedalion. I guess you already talked a lot about this. Mainly lighting, cable, of course. The participant needs to be in a good spot and you have to scan, and also the speed. Okay.
So yeah, maybe just one
yeah.
last statement on this,
Yes.
because we have to be a bit fuzzy on the mobile phone use, right? Which is kind of the most, I guess, appealing one, because you don't have to buy extra hardware and so on. And this is where we're also going to play around with it and try more. I would just refer to the papers that are already published on this. And I mean, why I'm pretty confident that it's going to work is because there are papers, like Field Trip Toolbox, and the paper that I showed free, Rob Cooper and Sabrina, so they did photogrammetry with phone, and you will find the actual accuracy that they were able to achieve. And so I'm pretty confident that our method, let's say in Cedalion, right, that generalizes this, doesn't really, the resolution in the end then comes from the scan that you put in. I mean, this is a general statement, but I think that as long as you're within the realm of what people use that have used phone-based photogrammetry for their scans, I'm rather confident that we'll eventually be able to, to perform, that this works with Cedalion as well. But we are also still playing around with some of the objects that we scanned, and to see, if it matches and so on. So basically, if you are now trying to run this all with photogrammetry based on phone, you might also get updates from us, because we have tested this only in a limited way, and there might be some small optimization that we will and can do.
Perfect. Thank you very much, Alex. Thank you very much, Eike, for the great presentation. If you still have questions, feel free to send to us, and we will make sure to get it to Alex and Eike. Thank you very much. See you on our next webinar. Bye-bye.